Actually, the problem at the moment is more one of explaining where the energy is coming from that powers the Earth's magnetic field.
To find out exactly how and where our magnetic field is generated, scientists need to explore the Earth's interior. But this isn't easy.
We really don't know a lot of detail about what's happening 2,000 miles down, because there's no way to send a probe there.
Since there's no way to probe it directly, scientists study the structure of our planet using one of nature's most powerful phenomena, earthquakes.
So seismologists, they wait for an earthquake, let's say in Japan, and then they put an array of detectors on the other side of the Earth and look for the sound going through the Earth. And by listening carefully, they can construct a map of what's inside the Earth.
Scientists measure earthquake vibrations called seismic waves. These waves don't travel through the planet in a straight line. Instead, they bend, changing speed and direction when they pass through different materials. By measuring these waves carefully, scientists learn that the Earth must be made up of distinct layers, like an onion. The surface layer, the crust, is made of solid rock, just a few miles thick. Below sits the mantle. It consists of denser semi-liquid rock. 1,800 miles down is the liquid outer core, a churning sea of molten iron and nickel. It surrounds the inner core, a solid iron sphere around the size of our moon that is as hot as the surface of the sun. Scientists believe that the magnetic iron core generates our magnetic field. But how?
People are easily confused by this idea that there's this big, solid iron inner core, so thinking it's just a bar magnet, it's just a permanent magnet frozen in that, and that's what causes all the magnetic field. But it's too hot inside the Earth. That can't happen. When the temperature gets hot enough, magnets turn off.
Permanent magnets stop working at 1,200 degrees Fahrenheit. So some other process must be generating Earth's magnetic field. To find out more, Professor Dan Lathrop embarks on a very ambitious experiment. At the University of Maryland, he and his team build a 10-foot mechanical model of the Earth's core.
The thing we want to understand is why some planets generate a magnetic field and why others have no magnetic field. So by building experiments, we could hope to understand the conditions of when it works and when it doesn't. What's the switch? Why sometimes a planet comes alive magnetically, and why sometimes they remain dead.
Inside this sphere is a solid iron ball, surrounded by 13 tons of churning liquid metal. Lathrop uses molten sodium instead of iron because of its lower melting point.
So we've got a rotating outer sphere, holds liquid sodium. It's meant to mimic the iron in the Earth's core.
Separate motors spin the inner and outer cores to mimic Earth's rotation.
Those drive the outer sphere up to about 4 revolutions per second, and the inner core up to about 15 revolutions per second. So let's go give it a spin.
If it succeeds, Lathrop's experiment will advance our understanding of how our magnetic field is generated.
Looks good. Seeing 26 tons of rotating metal and liquid up close in the sound, really had no idea it would be like that. It's rather intense.
As the vast sphere reaches maximum speed, something incredible happens. Huge lines of magnetism arc in and out of the model core.
While we can't see the magnetic fields coming out of the experiment, we can measure them. We can put many different magnetic field sensors and then map out these magnetic field lines coming out rotating, changing. It's fantastic.
Interactions between the inner and outer core create what's known as a dynamo. This generates a powerful, stable and self-sustaining magnetic field.
This is showing magnetic field patterns, red coming out of the experiment, blue going into the experiment. It's nothing like I imagined it would be.
Lathrop's mechanical core supports the theory that Earth's magnetic field is produced by a geodynamo in its interior. The motion of liquid metal in the outer core is vital to this process. The geodynamo depends on the flow of hot, molten metal in the Earth's core. Does Mars's cold core explain how it lost its magnetic shield?